Working in axis angle parameterization, we had these redundancies here, and now we can really get a picture of what SO3 looks like. So we can say each rotation, each element of SO3 corresponds to some vector, some 3 vector, which we define by combining this rotation angle and the rotation axis n. So we just take psi times n, and then all rotations are from a solid ball in R3, a ball of radius pi. So let's see here. This is SO3. And now by this choice here, that we now identify SO3 elements with points in this ball, we have immediately solved the problem with this redundancy here, because now the identity is just one point again. That's the point here in the origin. But what about the second redundancy? This really means that if we go to antipodal points on our sphere, they have to be identified. So this here means antipodal points on the surface, on the sphere. So the whole thing, SO3, is a ball now, and on the surface of the ball, on this sphere, the antipodal points are identified. This means SO3 is really homeomorphic to a real projective space. Now we see it's compact, and there are no boundary points here due to this identification. So it's a compact group. What about connectedness? Well, if we look at our sphere, maybe we can draw one again here. Looks more or less like this. No. This is our sphere. Then you can think of closed loops, maybe here somewhere inside or on the surface like this. This would be a closed path here in SO3, but you could also choose a point here and go right through the sphere and connect it to the point on the opposite side of the sphere. That's also a closed path. So SO3 is connected, but it's not simply connected, because we have these light blue path here, which cannot be contracted to a point.